Hi everyone, thanks for checking out this video. This is going to be the fifth video in this series I'm making on how to make neural networks from scratch in Julia. So if you guys have been following the series so far, we've been working with this value composite type that we're creating, basically these value objects that store numbers, and we want them to like automatically track the operation so that we can go back and calculate the gradients after doing like a series of operations. So this is the code that we have so far. We have our basic value type setup, our operation composite type for storing information about operations, both like the operation type as well as the args, which are the operands for that operation. Our basic value constructor, just some code to be able to print out the values, the equals comparison, our forward addition operation. This is the backprop for a leaf node, like a value that was just defined by the user and not created from any operation. So this just does nothing. And then we talked a bit before about this concept of multiple dispatch, which is the idea that in Julia we can use the same function name, like in this case backprop, but define it to do different things based on the type of the input. So with our values, we have this like op type like parameter of them, so we can tell what operation was used to create them. So like these ones are telling us that no operation was used to create them; they were just defined by the user. But here, this is defining what to do for a value that was created with an addition operation. So for example, if we have a val that's the sum of two other values, then this backprop function will be used to update the gradients of the operands for whatever value this is. So yeah, that's just a quick review. Hopefully you guys watched the last video, so that should be hopefully all review for you guys. So we said before that for our backward pass, we have this like internal backprop function that we call on each variable to update the gradients for the operands for whatever operation was used to create that variable. But this is like an internal function that the user doesn't actually call. The user just calls this one backward function on the last like resulting variable that they want to calculate the derivative of with respect to all of the inputs. So we were kind of working with this this example here. So let's say we have like w equals x plus y, z equals a plus b, and then c equals w plus z. So what we want our backward function to do, if it's called on c, is it'll go through like all of the values that have led up to this calculation of c, and it'll go in reverse starting with c, and for each of these values it'll update the gradients of the operands that were used to create that value. So this one here, backprop for c, it'll be updating w.grad and z.grad. You guys see here because these are the operands that were used to make c. And then it'll go back and do w. And for w, it'll be updating x.grad and y.grad. And then it'll do z, and for z, it'll be updating a.grad and b.grad. You guys following? Because these were the operands that were used to make z. And then for this one, a is one of these leaf nodes that we're talking about. So for a, it'll be this type of backprop function. So it'll just do nothing because a doesn't have any operands. So I'll just say like does nothing. B, another one of these leaf nodes, does nothing. X does nothing, and Y does nothing. So the goal for this video is to write this full backward function to be able to go through and do all of this. So that the user will just have to call backward on their last like output variable, and then it'll go back and automatically call all of these internal backprop functions to calculate all the derivatives of the final variable with respect to like everything that went into it at every step. Okay, so let's start trying to actually write the code for this backward function now. So we're going to say function backward, the input, we're just going to call it A. It's going to be a value, and then end. Okay, so now we can start filling this out. So for this part, I'm going to give credit where credit is due and reference Andrei Karpathy's SimpleGrad Python library, because the way I learned how to do this part is like directly from him and directly from his SimpleGrad tutorial video. So we're going to be implementing like almost the same thing that he's done here. So this part here in SimpleGrad, we're going to be implementing this almost exactly, except in Julia rather than Python. But yeah, basically we're going to be doing this thing called a depth first search, because, well, okay, I don't want to confuse you guys, so I'll explain first what we're trying to get and then how we're going to get it. So what we want to get is we want to get an array full of values. So we want to get a value type array where we want to get all of the values in order, like from the leaf, like the leaf node values, up to like the second layer values, and then the last one should be our final value. So it might look something like yeah, like y, x, b, a. Although these four could actually be in any order because these are all on the same like topological level. So these four could be in any order actually. But then they should all come before w and z. So maybe I'll just say like z, w, because these values are the operands for these two values, right? So it's going in kind of like the lowest level of like the leaf nodes up to the second level, and then the last one in here is C. So that basically, yeah. So that's what we're trying to get here. Let's put maybe like trying to get. And yeah, what I'm going to do here is I'm not going to like invent anything new. I'm going to use this thing called a depth first search. So yeah, this isn't something I invented. This is just like a classic like data structures algorithm, which is just a way of like if you have some node that you're starting with, and your node has pointers to other nodes, it's basically like a recursive algorithm you can use to get to like recursively call a function to get to the bottom first. And then once you're at the bottom, like start appending these bottom nodes to an array and kind of append all the bottom first and then kind of go upward from there. Yeah, a little bit confusing. Maybe this will be like a little challenge for you guys to like wrap your head around. It is like a recursive algorithm. But yeah, I didn't like invent this or something. This is just kind of like a classic algorithm. And I learned about it actually from Andrei Karpathy's tutorial. So yeah, this is basically the algorithm here. We just start with some like empty array. We keep track of the values we've visited so far that we've already seen, and then we have this like internal nested function, and yeah, we just kind of like keep track of the ones we've seen and keep calling this function recursively until we hit the bottom. And then when we're at the bottom, then we start appending them back into the list, like back upwards, kind of. So that way the result will be here that a value only shows up in this array if its operands that went into creating it have already shown up. So the order could actually be a little bit different too. It could even be something like it could be something like X, Y, W, and then A, B, A, be Z, because that would still be fine, because by the time we're seeing W, we've already seen the operands for W. And by the time we're seeing Z, we've already seen the operands for Z. And then by the time we're seeing C, we've already seen all of the operands that go into creating C. So that's just kind of like the solution criteria. We want to have it like an ordered array where by the time we see a value, we've already seen within the array like all of the operands that went into creating that value. Yes, that's like the solution criteria. So either of these would be like a valid solution. And basically this depth first search is going to be just like a recursive algorithm to guarantee that we're getting that kind of a solution. Okay, so I'll just start writing it for you guys, and then it's a little bit confusing. Like with all this recursion stuff, sometimes you have to like wrap your head around it a bit. But yeah, I'll just start writing it, and then hopefully you guys can either you'll understand it, or maybe you'll have to like kind of take my word and maybe try to wrap your head around it a bit. But yeah, I'm just going to start writing it, and hopefully you guys can like kind of follow along, or you may have to kind of take some time to wrap your head around it. And that's okay, because these recursive functions, yeah, can be a little bit confusing. But yeah, again, credit to Andre Karpathy, because I'm basically just going to copy like his code for this part. Yeah, so credit to him for that. So yeah, I'm just going to say function build topo, and it's going to take as the first input a value. It's going to be called v. V type value. Visited is going to be an array of type value. And then topo is also going to be an array of type value. So visit is keeping track of the ones that we've seen so far, and topo is going to be this final output list that we're going to be returning. So yeah, that's kind of the setup, and we're going to have this like internal like nested function like this to take care of that. Okay, so the first thing is when we see this value v, we're going to say if not v in visited. So what follows here is stuff we want to do if we haven't seen v so far, because remember we're thinking recursively. We're going to be calling this function again within the function. So this is all stuff to do if we haven't already seen v. So the first thing we're going to do is just push visited v. So just record that, okay, we hadn't seen it before, but now we have seen it. So just keeping track of what we've seen. And then the next thing is if v.op is not equal to nothing. Because remember, if v.op is equal to nothing, then that means that we've hit the bottom. So we don't need to. So basically, like these leaf nodes here at the bottom, their v.op would be equal to nothing because they weren't created from any operands. They weren't created from any operation of other values, in other words. So this is what we need to do if that's not the case. So if we're not at the bottom yet, if there is some v.op that isn't nothing, that means we're not at the bottom yet. So we need to say for operand in v.op.args. Remember, those are the arguments that went into making the value. So in that case, for w, this v.op.args would be x and y. So we're going to say, yeah, maybe I should be ending these two while on edit. Just keep track of where we're at. If operand is a value, just type checking it. Yeah, just type checking it, making sure we're dealing with the value. Then we're going to say build topo operand visited topo. So yeah, again, a little bit confusing. Recursion is always a little bit confusing, I think. So you might need to wrap your head around this a bit. But again, this is just a way of going down to the bottom. That's why it's called depth first search, because it's like before we add 1 to the topo list, we need to add all of the operands of 1. So then it's like, okay, we go to 2. But before we add 2, we need to add all the operands of 2. So we go to 3 and 6. But before we add 3, we need to add all of the operands of 3. So we go to 4 and 5. And when we get to 4, we see, okay, 4 doesn't have any operands. So now it's okay to add 4 because that means we're at the bottom. And then same with 5. 5 doesn't have any operands, so we can add 5 because that means we're at the bottom. And then after 4 and 5, then we can add 3 because we've already added all of the operands that went into making 3. So that's what this depth first search means, basically, is we kind of get ourselves to the bottom and then start adding the nodes to our topo array and kind of add them in a way so that we're covering all the operands before we add the result of that operation. So yeah, a little bit confusing. You guys might need to like wrap your head around the recursion and stuff, but yeah, maybe we can format this up a bit nicer now. Sorry, just remembering where we're at. Okay, so now once we get to the point where this is resolving false, where v.op is nothing, then we can start actually like adding these into our topo list again. So we can say at this point push topo v. So when will we get to this line? We'll get to this line for 1 if v.op is nothing. It'll finally like skip over this recursion step, like skip over this, and then finally add the value to the topo the topo array. And then also we'll even for the ones that do have operands, we'll get to this like on the way back up after the operands get added. So after 4 and 5 get added to the topo array, then the recursion will like go back up kind of and then eventually get to 3, so that 3 will eventually get added. And then once 3 and 6 are in, then 2 will eventually get added. And yeah, it's like with recursion, you might have to like wrap your head around it a bit. But yeah, eventually we will end up working our way back up through this whole thing. Oh, but also, of course, can't forget we need to return the topo so that it actually makes its way back up. Yeah, so this is good for our internal recursive function. Again, yeah, I know it's confusing. The recursion is always confusing. But yeah, this is good for our build topo function. At this point, if it works okay, we should have a list an array like this. Yeah, I was thinking before, I kind of got this a bit wrong. I think the order will not exactly be like that. I think the order will actually look more like this, because it'll be going in a way that I think if I'm getting this right, it'll be going like, okay, down this line and then 4, 5, 3, 6, 2, 7, 10, 11, 9, 12, 8, 1, I think. Maybe I'm getting this wrong. I don't know. This will be embarrassing if I'm wrong about this, but that's at least what I think. And then, yeah, if it is going that way, then the order in our example should look something like, yeah, like this, I think, right? Yeah. Anyway, all we need to be true for it to be a valid like solution is for it to be the case that we don't see a value until we've seen all of the values that were operands for that value. As long as that's true, then we're in good shape. Okay, so at this point we say topo equals build topo. A, remember A is our like final value that the user is calling the full backward pass on. So this should build out our topo. Okay, so now once we have like a topo array that looks like this, now what we do is we actually do this full backward pass that we're talking about. So we kind of go through the topo backwards. So this time when we're actually doing the internal backprop function, we're going highest to lowest. So we're starting with backprop on our final like output value, and then we're going backwards from top to bottom because we're using the chain rule. We're basically chain ruling our way through the calculus so that we can get the derivatives all the way back. So if that just to give you guys like the chain rule notation, it's like, okay, let's say we want the derivative of c with respect to x. So we're going to chain rule our way back. So we're going to say first, like this equals dc, the derivative of c with respect to w times, the derivative of w with respect to x, right? So that's how we like chain rule our way back. Say like 2x. So that's why we're kind of starting at the top and then going through from top to bottom like that, basically. So the way we're actually going to implement that is actually really easy. Oh, first, before we even do that, we just have to remember we have to set a.grad equal to 1, because remember all of the grads are set to 0 as like a placeholder. But for our final value that we're like calculating the derivative of with respect to everything else, we need to make that grad 1 just because the derivative of like anything with respect to itself is always 1, right? So we need to just set that to be 1 so that way, because remember when we're going back, when we're chain ruling our way back, it's always like incrementing by the val.grad for the operands. So we can't have it be 0, otherwise it's just going to be zeros going all the way back, right? So we need to have that be 1, right? But then after that, then we're just going to say for node in reverse topo, because the topo is ordered from like bottom to top, starting with the leaf nodes and going all the way up towards our like final value. For the actual backward pass, we want to go the opposite direction. We want to start with our final value and then calculate, like update the gradients of those operands for the final value, and then go back and do the middle layer and then update the gradients of those operands. So we're just going through this topo like backwards basically, and that's all we need to do. And from there, it's easy. We just say backprop for our node, because remember we've defined backprop to do different things depending on the type parameter of the value that we're passing in. So it's if it sees a value that was created from an addition operation, it's going to update the gradients of the operands like this. And if it sees a value that was not created from any operation but was defined by the user, then it's just going to do nothing, because those are like the leaf nodes basically that don't have any operands to update the gradients of. Okay, I think this should be good. Okay, I think we're ready to test it out. Let's just I think I forgot to actually run this, so let's just run these functions to make sure that we have them. And then let's actually try out our example. So this was kind of some notes, but let's actually try out this example. So we'll say you'll say like x equals value 2, y equals value 3, a equals value 1, b equals value 4. You guys could be making these floats too, or like decimals if you want to. This could be like a decimal like that if you want to test it out. I'm just keeping it simple just to make it easy, but I mean, whatever. And then, okay, intermediate step, w equals x plus y, z equals a plus b, and then c equals w plus z. And then do our full backward pass on c. And then hopefully that should update the gradients of everything. So we should have, and they should all just be 1 because it's all addition, but Yeah, it should give us 1 for all of them. So then we can print them out like print line w.grad, which is dcdw, z.grad, dcdz, okay, a, b, x, y. Remember, this is remember, just to emphasize the point here, this is not the derivative of z with respect to a. This is the derivative of c with respect to a. And this is not the derivative of w with respect to x. This is the derivative of c with respect to x. Because it's the derivative of the final output value with respect to everything that went into it. So yeah, we can, yeah. And I think this should just all be 1, right? Yeah, because it's all addition. Yeah, so these are all 1. Although we also talked before about like a more complicated example. So this was the rationale for why we had like why we're incrementing rather than just setting the gradients, because it could be that a value is used in the sequence of calculations more than once. So we had like another more complicated example where we said like, okay, x equals value to y, or sorry, I'll make this something else just make a point here. Y equals value for z equals x plus y, w equals z plus x. So now x has been used twice here. So actually, even though it's all addition, since x has been used twice, it should actually be that the derivative of w with respect to x is 2, right? Because increasing x by 1 will cause w to increase by 2 because x has been used twice. So if we print out now, or sorry, we first do our backward pass on w. Now if we print out x.grad, it should be 2, right? Because backprop, our internal backprop function is hitting x twice to update the grades. It's updating this once when it hits yeah, it's updating this once on the backprop of w because x is an operand for w, and then it's updating x.grad again on the backprop of z because x is a operand of z. So this should be 2, I think, right? And yeah, looks like it's getting it right. Yeah, okay, looks like it's working. Okay, so I think that's going to be it for this video, and I have some good news for you guys actually. So the good news is that if you've understood everything up until this point, then you're already past the hard part. Basically, we've done the hard part already. These past 2 videos, like understanding the chain rule and backpropagation and how to like update the gradients with this like operation tracking we're doing, that was already the hard part. So I know it might seem like we have a lot more to do because it's like so far we've only done addition, right? Like we haven't even done anything with a neural network yet. We've only just done this like derivative calculation for addition. We haven't even added any other operations yet, right? But actually, this concept we just covered in the past 2 videos, that was the hard part. From this point on, it's going to kind of be all downhill from here because all we have to do from this point is just keep writing some more functions like this for any operations we want to add. And then the concepts are going to be the same. Like we're going to eventually add like multiplication, division, subtraction, stuff like that. But the concepts are like always going to be the same of just writing some kind of function like this to define what to do for the forward pass of the operation, and then defining something like this for how to update the operands on the backward pass. So from here, it's just going to be adding more of these operations, but we've already covered all the difficult concepts. And even when we get to tensors, I know we haven't even gotten to tensors yet, which might seem like we still have a long way to go because when we're eventually going to be doing the actual neural nets, that'll be with tensors. But tensors, like when we get to tensors, it's still going to be these kinds of concepts, just defining like operations, like the forward and backward passes like this, and then updating the gradients the same way, except it's going to be like the arithmetic will be more complicated because it'll all be like matrix arithmetic, like matrix multiplication and matrix addition mostly. So it'll be like more complicated arithmetic, but the actual concepts of the operation tracking and like the forward and backward passes here is all going to be the same, and it's all going to be just kind of continuing to do this stuff that we just did in the past 2 videos. So yeah, that's the good news. Is if you guys have understood everything up until this point, then we're already past the hard part. From here on, it's just going to be like adding out more of these functions to let us do more and more things with our values, and then eventually making our tensor composite type, which will just be almost exactly the same as the values, except we'll be doing arithmetic with arrays, like 2-dimensional arrays, rather than scalar values. So yeah, that's the good news. Is we're already past the hard part, so it should be kind of easy from here on. But yeah, thanks for watching, guys, and just a reminder, all this code will be up on my GitHub. Also, just another reminder, this whole video series is based on this Julia package that I made called SimpleGrad. So this is like a really usable package that I made. You guys can like install it and use it and stuff if you want to. And this whole series is just showing you guys like how to build this package like from scratch, basically. Because it's meant to be like an educational package. There's like an under the hood section, which is like kind of like a textbook chapter explaining kind of the same thing that these videos are explaining. Yeah, it's supposed to be like an educational package. Also have the GitHub link up here. So yeah, you guys can check that out if you want to. But yeah, the next video, I think we'll just keep building out this value type so we can do more and more things with it. So yeah, thanks for watching, and I'll see you guys next time.